Hello everybody, my name is Danielle Weigel, and today we are going to be continuing solving example problem 1.17 for the class Transport 2 for exam 1. This follows after my first video in which we discussed scaling and how to create our initial guess for molar flux that's going to have a reasonable order of magnitude. So first I'm just going to go over the steps that we're going to take to solve this problem, because then we have to import a couple of tools that are going to help us. We have our driving force equations and we have our initial guesses for our molar flux, and then we also have the initial values for mole fraction at eta equals 0. So what we're going to need to use a solving initial value problem function. So that's something we're going to have to import, and the way that we're going to return our values for those mole fractions is with an array. So we also have to import a tool for that. And then after we use our solve IVP initial value problem function, what we will be getting back is a function that we can use to calculate our mole fractions using eta from 0 to 1. But those values aren't going to be initially correct since our mole fraction values aren't correct. So then what we will need to do is use a root solver, because we know that at eta equals 1, the mole fractions of component 1 and component 2 should be equal to 0, because that's at the top of the Stefan tube where air is blowing across. So the mole fraction there should be 1 for air, which is component 3. So we'll use that root function in order to determine our actual molar fluxes of components 1 and 2, and then we can pop that into our equation again for our solve IVP function, and that will give us our function that we can use to calculate the actual mole fraction values across the distance from z equals 0 to delta or eta equals 0 to 1. So now that we've discussed how we're going to approach this problem, we need to import a couple of tools that is going to help support our code. The first thing that we have to import is going to help us out with the functionality of our arrays that I mentioned earlier. So we need to import numpy, and then we have to import our solve IVP function, and that is in the scipy integrate library. And then also from the scipy library, this time from the optimize section, we have to import that root solver. And once we have that final function that we can use to calculate our mole fractions from z equals 0 to delta, we want to actually graph those out so that we can show them visually. So we also have to import a couple of tools that are going to help us with the graphing. So from Plotly, we need to import make subplots, as well as we need to import the ability to actually graph our arrays, our outputted arrays, onto the figure that we're making. So we need to import graph objects, and we'll just call that geo for graph objects. And then we also need to import, if we want to make our graph look nice and pretty, or for me, because I like using a dark background instead of a light background, it's easier on my eyes, we can also import templates for that. So in order to do that, we use plotly.io. And then we can go ahead and just set the dark background as our default background. So then we will use pio dot template dot default, and then we are going to set that equal to Plotly Dark. And as long as I typed everything right, we should be able to Shift Enter and run that and have no errors, and it looks like I did that correctly. So then we can go ahead and move on. Now that we have all of our tools imported into our code, we need to define all of the variables that we know that we are going to use within these equations. So I already have our known variables. We have our Maxwell Stefan diffusion coefficients for each of the components. We have the pressure, the temperature, the gas constant, and then we also have our molar concentration, which we already defined as pressure divided by the gas constant times temperature. And then we have delta on here, as well as our initial guesses for our molar fluxes, and then our initial values for our mole fractions at eta equals 0. We are also going to include the definitions for F12, F13, and F23 on here that we discussed earlier, just to make writing the equations easier, or driving force equations easier later. So we can define that as the molar concentration times the Maxwell Stefan diffusion coefficient divided by delta. And that is the same for all three of these. And then F23. And with that, that defines all of our initial variables that we need to define. So as I mentioned before, the first thing that we're going to do is use our initial value problem solver, but in order to do that, we have to first define the functions that we're going to use. So first, we're going to define our driving force equation. So we will call our driving force equation dy, and our independent variable is eta, and our dependent variable is the mole fractions. And that's going to output as an array. So the way that we're going to end up writing it, I'll write out the equation first and then we'll discuss it. We are going to write this out as an equation of an array. And in the first section of the array, we are going to have the mole fraction of component 1. And the second part of the array, we're going to have the mole fraction of component 2. In order to do that, we need to use our numpy array command, and then we just have to type out what our driving force equations are. So for the first component, like we discussed earlier, it's going to be the mole fraction of component 1 times the molar flux of component 2 minus the mole fraction of component 2 times the molar flux of component 1, and then that is divided by F12. I need to add in another parenthesis here. And then we are going to subtract from that the interaction between 1 and 3, which ends up just being y3 times the mole fraction of component 1 divided by F13. And then we can write out our driving force equation for component 2, which is very similar to component 1, y2 times n1, the mole fraction of component 2 times the molar flux of component 1, minus the mole fraction of component 1 times the molar flux of component 2, and then all of that is divided by F12 again. And then once again, we are going to subtract the interaction between 2 and 3. So that comes out to be the mole fraction of component 3 times the molar flux of component 2 divided by F23. And that should be correct. We'll find out later. And as I mentioned before, this is going to output as an array. We already discussed driving force for component 1 is the first half, and the driving force component 2 is in the other half. So we'll have to define our y1 as that, and the first slot in an array is 0, and for component 2, it will be in the first slot, one slot. And then since we only used the driving force equation for 1 and 2, we didn't need to write out the equation for 3 because we don't need to use that here. We can just define y3 as equal to, or the mole fraction of component 3 as equal to 1 minus the mole fraction of component 1 minus the mole fraction of component 2. And once we have that function defined, we can go ahead and call our solve IVP function in order to look at what the function is originally going to give us with our initial guesses. So we will call this first one res for result, and then that will be equal to solve IVP that we imported earlier. And the first thing we have to input is our function, which we defined as dy, and then the span for the independent variable, which is eta, and we want that from 0 to 1. And then we have our initial values that we're using, which is y1i and y2i. And then we also have our method. We are going to be using the Rodot method, if I could spell correctly. There we go. And then we also need to set our dense output to true, so that we are solving all the way from eta equals 0 to 1, all the way across that spectrum. So now that we have our solved IVP function written out, what we have to do is look at this equation, and it's utilizing the molar fluxes of component 1 and component 2, but we haven't defined that yet. And so what we are going to define that is initially as our initial guesses. So n1 is going to be equal to n1i, and n2 will be equal to n2i. So as long as everything is typed in, we can then go ahead and look at our function. I forgot a colon right there. That happens. So then we can go ahead and look at, this is our function right here. So we can't directly look at that, but then we have a preview right here of what the outputs are, and we can see that the mole fraction of the first component ends up becoming negative, where the mole fraction of the second component ends up increasing, and we know that that is wrong. To further get an idea of how incorrect this is, we can type in res.sol, which pulls that function at eta equals to 1, which we know is supposed to be 0. And that outputs as a negative in 0.86, which we know is incorrect. But that's okay. That's what we were expecting because we know that the molar fluxes that we used are just our initial guesses. They're not correct. But once again, since we know that at eta equals 1, those two mole fractions are supposed to be 0, we can then use a root solver to figure out what our actual mole fractions are. So the first thing that we have to do is define a new function for our roots and the molar fluxes. So we just shifted everything in so that this will fall within the same function, and we're going to find this as f of n, since that is what we are using, and that's what we're trying to solve for. And we can't forget the colon, and then just like we did before, that n is going to output as an array, with the 0 slot being the molar flux of component 1 and the 1 slot being the molar flux of component 2. So we have to write that out as well. N1 will end up being this right here, and the molar flux of component 2 is going to be this one right here. And then what we are going to end up returning is that res dot sol of eta equals to 1. And that is because we know that those should be equal to 0 in our in what we're going to use for our root solver. So now that we have that defined, we can also create a new variable that's going to use our root solver. So I will call this one res n for the result of the molar fluxes, since that's what we're using the root solver to solve for. Then we can call the root function, and the first thing we need is the actual function we're using, which we defined as f. And then we need our initial guesses for what we think the molar fluxes are going to be. And we already know that those are n1i and n2i. And this should be in brackets because it is an array. And with that, let's call that and see what we get. Oh. Aha. There we go. I love, you know, all those functions. So we need to make sure that our new variable is not falling under the function that we previously defined. Anyway, so as we can see from here, the output is in terms of 10 to the negative third for component 1 and component 2. Those molar fluxes are within the order of magnitude 10 to the negative third. So we can assume that those are correct. So then we can also redefine our molar fluxes. We know that n1 will be the result of this res n function with x, because that pulls up our solutions in the 0 of the array. And then n2 will be res n in the 1 spot. And that will give us our new molar fluxes. So once we have that, we can go ahead and plug them back into our solve IVP function that we were discussing earlier. So I'm just going to copy these over. And we need to backspace these because tabs are important and will mess up our function, as we learned a little bit ago. So we have that. We already have our new n1 and n2 defined up there. So with that, we should be able to look at our new solution. And as we can see, these are approaching 0. Let's go ahead and call eta equals 1 to see what that gives us. And those numbers are pretty darn close to 0. So I would say that we are on the right track. Now that we have this new equation defined, we want to graph it so that we can visually see what the mole fractions are from either z equals 0 to z equals delta, or from eta equals 0 to eta equals 1. And when we're graphing this, we want the output to be on an evenly spaced set of numbers because we're going to plot it like a scatter plot and then connect the lines. So what we first have to do is create an array of evenly spaced numbers. So since we are using eta in our function, we will call this one eta plot because we are going to use that array to plot out our mole fractions. And we are going to use the numpy linspace command to create that array. And we want to go from 0 to 1. And let's just go with 50 different numbers. Once we have that, we need to create an array with using those that array of numbers that we already have, and using those in our solve IVP function to get the corresponding mole fractions. So we are going to define a new variable. I'm just going to call it comp for the mole fraction composition. And then we need to do the same thing that we did before when we were just looking for values, res.sol, and instead of plugging in 1 for eta, we are going to plug in all the numbers from the eta plot. And that will create our new array of variables for the mole fractions. So then once we have that, I'll do this in a new one, we need to create our actual figure that we're going to plot on. So in order to do that, first we have to actually create the fig, and then use make subplots. And since we want everything graphed on just one graph, we can set the rows and columns to 1. And then we need to add on our traces. So fig add trace, and then we used go, and x should be equal to our eta plot. And since we want this back in terms of meters, we're going to use eta plot times delta. And then for our y, we want our y to be equal to the mole fraction in that array that we saw for comp, and it's for component 1, so that will be comp 0. And then we also need to add a name for that trace, and the first component is acetone, so that's what we'll add for that name. And after that, we need to add on the other ones. Looking at that command, we also need to go.scatter because we're using a scatter plot, and instead of this, it is this parentheses. I think that's correct now. And now we just need to add on our other two traces. So what we're going to do is just copy this command that we already wrote out and copy it down. And then we want to do component 2, which just uses the comp variable that we already used. And then this is methanol. And then our third component is air. And we defined that already as 1 minus the mole fraction of component 1 minus the mole fraction of component 2. And with that, that should give us our plot. Make subplots is not defined. That leaves subplots, import make subplots. Oh, I didn't spell it right. Subplots. There we go. And there we go. That creates our graph showing the composition of the mole fractions across z equals 0 to z equals delta, which is 0.28 or 0.24. Delta is 0.24 meters. And as you can see at the end, our air mole fraction comes up to 1, as we know, and the other two reduce down to 0. So there you go. That is how we determine the molar fluxes of the system, as well as the mole fractions from z equals 0 to z equals delta, or eta equals 0 to eta equals 1. I hope this helped. If you have any questions, feel free to leave them in the comments below, and have a great night, everybody.